Please pause the video and try this problem. And now let's discuss the problem together. Now we can start by numbering our carbons. Then we want to try to identify roles. There are no formal charges present. No metals, no ionic bonds, no formal charges present. So what can we identify here? Well, neutral iodide, we've memorized, is a good leaving group. And who are we going to use as our nucleophilic atom? Well, there's nobody with a negative formal charge, so we'll have to look for a neutral nucleophile. Oftentimes for a neutral nucleophile, we want to look for an atom with a lone pair. Well, neutral oxygens have lone pairs. So it looks like we're going to use this neutral oxygen with its lone pair as our nucleophile. In the first video in this series, we saw that when there's no negative formal charge, a neutral atom with a lone pair, such as neutral oxygen, can be used as the nucleophile. So that's what we're going to do here. We can identify our alpha carbon is carbon 2 because that's the carbon that is attached to the leaving group. Now let's identify the mechanism. And the way we identify the mechanism is with our table. To choose a row, we have to decide if our alpha carbon is primary, secondary, or tertiary. You should write down that you have a tertiary alpha carbon here because carbon 2 is attached to 3 other carbon chains. Remember that even if a carbon, even a single carbon could be considered a carbon chain for purposes of this definition. So bottom row because we have a tertiary alpha carbon. And we choose the column based on our nucleophilic atom. Well, we're using a neutral oxygen. And neutral oxygen will put us in this left-hand column. Neutral oxygen, that's the poor nucleophile column. You can see that water is specifically listed as one of the possible poor nucleophiles for this column. And that tells us that the major mechanism will be SN1. Write down the name of the mechanism. E1 is a minor mechanism here, but I meant to write the problem to ask for the major mechanism. So if the problem is asking us for the major mechanism, we'll just focus on the SN1 and not worry about the E1 for the time being. Notice how crucial it is to think about the formal charges. Here we have a neutral oxygen. Notice that a negative oxygen would put us in a completely different column and give us a completely different reaction. There's a huge difference between neutral oxygen in the poor nucleophile column, which would give us an SN1 reaction here, and negative oxygen in the good nucleophile strong base column, which would give us an E2 reaction here. The most important factor in organic chemistry is the formal charges, so it's crucial that we recognize that this is a neutral oxygen, not a negative oxygen. Neutral oxygens, like in water and alcohol, are poor nucleophiles. Negative oxygens are good nucleophiles and also strong bases. All right, so now we know this is going to be an SN1 reaction, and now only now can we draw the electron pushing arrows. It's useless to draw the electron pushing arrows until you know the name of the mechanism. Do you remember how to draw the arrows for an SN1 mechanism? Remember how many steps are there? 2 steps. And what happens in those steps? Here's what we've memorized happens in the steps for an SN1 reaction. First step, the leaving group leaves the alpha carbon. We show the arrows for that like this. Remember that a leaving group receives electrons as it leaves. That's the only arrow that we need for the first step. It might seem weird that the leaving group leaves on its own without being pushed, but that's the way it works in the first step of an SN1 reaction. So now we can draw the products from that step. The arrow tells us to break the bond between carbon 2 and the iodide. But the most important part to get right is the charges. Remember that we changed 2 charges. We changed the charge on carbon 2 at the beginning of the arrow. Carbon 2 started neutral and it lost electrons, so carbon 2 became positive. And the iodide gains electrons at the end of the arrow. The most common student mistake here is to forget this positive charge. Now, are we done? Are we done with the mechanism, or do we need another step? Well, we're probably not done because our main product still has a formal charge, and we expected another step anyway, a step where the nucleophile joins the alpha carbon. We've already labeled that this is the nucleophile. We'll label carbon 2 as the alpha carbon. Now it's called the alpha carbon because it's the carbon with the positive charge. And we draw the electron pushing arrow from the nucleophile, the electron donor, towards the alpha carbon. That's the arrow for this step. Nucleophile joins the alpha carbon. Now we draw the products from that step. This arrow tells us to draw a bond between the oxygen and carbon 2. Here I've drawn the bond between the oxygen and carbon 2. What about these hydrogens? Should these two hydrogens still be bonded to the oxygen? Absolutely, because they were covalently bonded. These hydrogens are covalently bonded to the oxygen because everything here is a non-metal. Well, we never break a covalent bond unless there's an arrow that tells us to break it. In the SN2 series, we discussed that we only break a covalent bond if there's an electron pushing arrow that tells us to break that covalent bond. Well, there's no electron pushing arrow telling us to break the covalent bond between the hydrogens and the oxygens. Notice that an arrow that tells you to break a bond looks like this. If the arrow tells you to break the bond, it's because the tail of the arrow is on the bond. When the tail of the arrow is on the bond, that tells us to break the bond. Well, the tail of this arrow is not on the covalent bonds, it's on the lone pair. So this arrow does not tell us to break any covalent bonds, so it would be a big mistake if we didn't pull along these hydrogens. Now, the most important part of this picture to get right is the formal charges. This oxygen is at the beginning of the series of arrows, so this oxygen has to change its charge. This oxygen is losing electrons from the first arrow. The oxygen began neutral, and it's losing electrons, so the oxygen should become one step less negative, one step more positive, so this oxygen ends up with a positive formal charge. The most common mistake that students make on this step is forgetting to put in this positive formal charge. My experience is that students have a really hard time remembering to change the formal charge on this first atom. Did you remember to do that? When you did this step, did you remember to change the charge on this oxygen from neutral to positive? If you did change the charge, great. But if you didn't, then you need to keep working on this idea. Always make the atom that loses electrons from the first arrow one step less negative, one step more positive. It's absolutely crucial to change this charge from neutral to positive. And of course, carbon 2 is at the end of the arrow, so carbon 2 should also change its charge. Carbon 2 started positive, and carbon 2 is gaining electrons, so carbon 2 changes from positive to neutral. I've actually already shown that. So again, really focus on this idea. The most common mistake would be forgetting to change the charge on this oxygen. Remember, the most important part of the picture to get right is the formal charge. Formal charge is not a minor detail. It's the most important part of our answer. So we've now done the two steps for SN1. We've done our two SN1 steps. So are we done? Or does it seem like we need another step in the mechanism? Well, even though we've done our two SN1 steps, it seems like we're not done. It seems like we're not done because our main product still has a formal charge. Remember that usually the reaction is not done until the main product is neutral. So it looks like we're probably not done. That's why it was so crucial to get this positive formal charge. If you forgot the positive formal charge, then this would seem like an acceptable final product. It's only if you remember to change the charge on this oxygen that you can see this is probably not an acceptable final product. A mechanism is usually not finished when the main product still has a formal charge, although there are some exceptions to that, such as SN2 reactions. So what do we need to do to get rid of this positive formal charge? It seems like we've already completed the main steps for the SN1 reaction, so what kind of step can we execute now to get rid of this positive formal charge? And the answer is we need to do something that we could call an acid-base cleanup step. If you execute the main steps of the reaction and you still have a positive formal charge on the main product, what we usually do is execute an acid-base cleanup step. Let's put that in a little context here. So what types of steps have we done so far? So here for step 1, we could call step 1 a leaving group step, or a leaving group only step. A leaving group step because the only thing that participates in this first step was the leaving group. Then here for step 2, we could call step 2 a nucleophile electrophile step, because this is the step where the nucleophile attacks the electrophile. I suppose I should have labeled here that carbon 2 is acting as the electrophile. What's the clue that carbon 2 is a good electrophile? The clue is that carbon 2 is a carbon with a positive formal charge. We should have noted that before. And now that we've done that nucleophile electrophile step and we still have a positive formal charge, we're going to do step 3, and we can call this an acid-base cleanup step. Acid-base cleanup step. Now, who are we going to use as the acid and who are we going to use as the base? Well, we should focus first on the atom with the formal charge. The oxygen has a positive formal charge, and we know that having a positive formal charge makes an atom acidic. An atom with a positive formal charge can act as a strong acid. Because acids receive electrons, and a positive charge makes you want to receive electrons. So actually, let's label this as a strong acid because of the positive formal charge. So now we need to identify a base to react with this strong acid. Who should we use as our base? Now, your first instinct should probably be to use the I- because it has a formal charge. Our first instinct is to use the atoms with formal charges. So our first instinct might be that because of the negative formal charge, the I- will be a good base to use. But we specifically learned in the previous video that actually I- is a very weak base. I- is a very weak base. So we would only use I- as a base if there was nobody better around. And in fact, we learned in the previous video that we usually prefer to use water as a base rather than I-. So I'm going to draw in a water molecule to use as the base. And be specific, specifically it's the oxygen atom that's going to act as our base, because the oxygen is a neutral atom that has a lone pair. Now, we learned that water is a weak base. Water is a weak base, but even though it's a weak base, it's still stronger than I-. So most professors would prefer for you to use water as your base in this step rather than the I-. Again, we covered these ideas in the previous video. I-, Cl-, Br- are very weak bases. So when water is the solvent, we usually prefer to use the water as the base rather than I-, Br-, or Cl-. That's the approach that most professors would prefer. Now, water is a weak base, but it is still, but that's okay because this molecule here with the positive charge is a strong acid. We only need one of these reactants to be strong, so to speak, for the reaction to work. So a strong acid can react with a weak base. We saw in the previous video that a strong acid can react with a weak base. Only one of the starting materials has to be strong in order for an acid-base step to occur. Now you might worry that we already used up the water in step 2. If we already used water in step 2, how can we use water again in step 3? Well, again, we discussed that in the previous video. Remember, water is the solvent for this reaction, and the solvent is generally present in far greater quantity than the other starting materials. So you don't need to worry about running out of the solvent. Even if we've used a solvent molecule in one step, there will be plenty of solvent molecule left over for using again in later steps. So it's perfectly okay to use the solvent in one step and then use another molecule of the solvent in a later step. The solvent is generally present in far excess of the other starting materials. Now, do you know how to draw the electron pushing arrows for this step? I hope it was boringly easy for you to draw the electron pushing arrows for this step, although that is something that gives many students difficulty. You should have memorized that the first arrow for an acid-base step points from the base towards the proton. So we begin the arrow from the base, and it should point towards one of these protons on the oxygen. Now we have to separate these two hydrogens to draw this correctly. Separate the two hydrogens and draw this bond. This is not correct. This is not correct. Once we draw the bond, we should draw the two hydrogens separately. So that's what this first arrow looks like, from the base towards the hydrogen. Because a base, remember, a base donates electrons to take a proton. This is the arrow to show a base donating electrons to take a proton. And then we need another arrow for the role of the acid. The next arrow will point from this bond towards the oxygen. It should make sense that the arrows end on the positive formal charge. We like to put a positive formal charge at the end of the series of arrows. Notice how this arrow shows the acid gaining electrons to lose a proton. An acid gains electrons to lose a proton. So these are the correct arrows for the acid-base step. So notice that we are using water twice in this mechanism. We use the water first as a nucleophile, and then we use the water again as a weak base. That's consistent with our table, isn't it? Because here's water, and notice that water is in the column for both poor nucleophile and weak base. Water is a poor nucleophile, but still good enough for SN1. And the table also tells us that water is a weak base. So we're also using the water here as a weak base. It's only a weak base, but that's still good enough to react with a strong acid, such as this. So our table confirms that we can use water both as a nucleophile for SN1 and as a weak base. Now we can draw the products of that step. Please notice the order in which we carry these things out. First, we wrote down the roles, strong acid and weak base. Then we wrote down the electron pushing arrows. And only then do we draw the products. Do not try drawing the products until you've finished drawing the electron pushing arrows for this step. And do not try drawing the electron pushing arrows for this step until you've labeled the roles. That's generally the best habits for a beginning Ochem student. Now, this arrow tells us to form a bond between the oxygen and this hydrogen. I'll just write this now as H3O to show that the oxygen has a new bond to a new hydrogen. Now remember, the most important thing to get right is the charges. Since the oxygen is at the beginning of the arrow, we have to change the charge on this oxygen. The oxygen started neutral and it lost electrons, so the oxygen becomes positive. The most common student mistake would be forgetting to change the formal charge on this oxygen, but if we forget that, that's a bad mistake. Now this arrow tells us to break a bond between the oxygen and this hydrogen. So here we show that the oxygen has lost one of its bonds to hydrogen, and therefore the oxygen only has one hydrogen left. Again, we have to change a charge. This oxygen started positive and it gained electrons, so the oxygen should end up neutral. Remember, for every mechanism step, we change two charges at the beginning and end of the series of arrows. At the beginning and end of the series of arrows. We never change the charge in the middle of the series of arrows, so we don't change the charge, say, on this hydrogen in the middle of the series of arrows. Just here on the oxygens at the beginning and end of the series of arrows. Now, does it seem like we're done, or does it seem like we need another step? Well, remember that the mechanism is usually finished when the main product has no formal charges. Well, this is what we would consider the main product of the reaction. And we did get to the point where this main product has no formal charges left. So it looks like, yes, we're done with the mechanism. Now notice we couldn't get rid of all the formal charges. We still have a formal charge here, and we still have a formal charge here. You often can't expect to get rid of all the formal charges, but as a problem-solving technique, if your main product, so to speak, has no formal charges, that's often a good sign that you've finished the mechanism. This is an especially useful rule for first semester problems. Remember, there are some exceptions to this. In fact, SN2 reactions can be an exception to this rule. We saw in the SN2 series that if you do an SN2 reaction with a neutral nucleophile, that will usually end with a positive formal charge on the main product. But that's an exception. Here we're going to follow the general rule that our final main product has no formal charge. Here's a new updated checklist of things to do for each mechanism step. Now this version of the checklist is specifically designed to describe things that you will do for each step after the first step, because there's some extra actions that you have to take for the first step, like determining that the reaction is SN1 or SN2. But obviously most of these actions also apply to the first step. Anyway, the big new thing I've added to the checklist is you should now try to get into the habit of determining what type of step you're going to be carrying out. And the types of steps that we've seen so far are nucleophile-electrophile steps, leaving group steps, and this new acid-base cleanup step. So notice here how we've labeled step 1 was a leaving group step, because only the leaving group participated. Step 2 was a nucleophile-electrophile step. And step 3 was our acid-base cleanup step. Do you see why this is called a cleanup step? What are we cleaning up? We're cleaning up the positive formal charge. This is called an acid-base cleanup step because it's cleaning up the positive formal charge on our main product. Now, the reason that it's useful to label the type of step that you're going to be carrying out is obviously because that helps you to predict the electron pushing arrows, but also that will help you to start getting a feel for the rhythm of organic chemistry reactions. There's a certain rhythm to organic chemistry reactions, certain patterns of steps that occur a lot. For example, a common pattern is if you do a nucleophile-electrophile step and you end up with a formal charge on the main product, you oftentimes or usually follow that with an acid-base cleanup step. So we want to get comfortable with this pattern. If you carry out a nucleophile-electrophile step and there's still a formal charge on the main product, oftentimes what you need to do next is an acid-base cleanup step to clean up that formal charge. So by labeling the types of steps, we'll start to get comfortable with recognizing that common pattern of steps in Ochem mechanisms. So I encourage you to start trying to add this to your checklist. Get in the habit of identifying what type of step you're carrying out for each step in the mechanism, and then you'll start to see the common patterns that appear in Ochem mechanisms, like following a nucleophile-electrophile step with an acid-base cleanup. Of course, we carried out these other steps like labeling the roles that atoms would play, such as strong acid and weak base here, or nucleophile, electrophile, and leaving group. We drew the electron pushing arrows. Then we drew the products after we had drawn the electron pushing arrows. We determined when we were finished because by checking to see whether our main product still had a formal charge. Please pause the video and try this problem. I hope you did try this problem on paper. Now let's discuss it. Here's a checklist of actions to carry out for the first step in a mechanism. The things that you do for the first step in the mechanism are a little bit different than what you do for the second or third step. So here's some actions to take for the first step. Let's make sure we've numbered all the carbons in the starting materials. Including this one. Look for ionic bonds. Well, there are no metals here, so there are no ionic bonds and no formal charges that we need to draw in. Now we can identify roles. For a nucleophile, first we would look for a negative formal charge, but since there are no negative formal charges, we'll use this neutral oxygen that has a lone pair. We know that a neutral oxygen in an alcohol with a lone pair can be a nucleophile. So I'll label that role. And we have memorized that neutral bromine is an acceptable leaving group. So those are some of our roles, and we identified the clues for those roles. Label the alpha carbon. Our alpha carbon here is going to be carbon 3, so we should label whether it's primary, secondary, or tertiary. This is a tertiary alpha carbon because carbon 3 is attached to 1, 2, 3 other carbon chains. Now we have to determine the mechanism using the table. We're in the bottom row of the table because we have a tertiary alpha carbon. And our nucleophile is the neutral oxygen in an alcohol. Neutral oxygen in an alcohol, which puts us in the left-hand column. So the major mechanism will be SN1. Our major mechanism will be SN1. Again, notice that if we had a negative oxygen, the mechanism would be completely different. So focus on the formal charge. Here we have a neutral oxygen. We know it's neutral because all its bonds are covalent to other non-metals. So the mechanism is SN1. Make sure you actually write down the name of that mechanism. So we used the table to determine that the major mechanism is SN1. Back to our checklist. What type of step are we going to do first for an SN1 mechanism? Well, you should have memorized what happens in an SN1. We have memorized that the first thing that happens in an SN1 is the leaving group leaves the alpha carbon. So we expect to begin here in step 1 with a leaving group only step. So now we can draw the electron pushing arrows for that step. Here's what the electron pushing arrow looks like for a leaving group only step. The leaving group receives electrons to leave the alpha carbon. Now we can draw the products of this step. Notice that we don't try to draw the products until after we've drawn the electron pushing arrow. This arrow tells us to break the bond between carbon 3 and the bromine. I broke the bond between carbon 3 and the bromine. I was careful to number all of these carbons. But the most important part to get right here is the formal charges. We should change 2 formal charges at the beginning and end of this arrow. Carbon 3 is losing the electrons from this arrow. Do you see how carbon 3 is losing the electrons? Carbon 3 used to be sharing these electrons in a covalent bond, but now the electrons are moving into a lone pair on the bromine, so carbon 3 is losing those electrons. So carbon 3 should become 1 step less negative, 1 step more positive. Carbon 3 ends up with a positive formal charge. And the bromine started neutral and gained electrons, so the bromine ends up with a negative charge. The most common mistake that students make is forgetting to change the charge at the beginning of the arrow. But if you don't put in this positive charge, the rest of your mechanism won't make sense. Now we have to decide whether we are finished or whether we need another step. Well, since our main product still has a formal charge, we expect that we're not done with this mechanism yet. Also, there's another step for SN1 that we have to do. So now we'll move on to the next step. Now remember, this was our checklist of things to carry out for the first step in the mechanism. Here's a slightly shorter checklist of actions to take for each step after the first step. Now again, we have to decide what type of step we're going to carry out for step 2. Well, we expect that step 2 of an SN1 will be the nucleophile attacking the alpha carbon, and therefore we expect that step 2 will be a nucleophile electrophile step. Now that we've determined the type of step, we can identify the roles that atoms will play. We've already identified that this oxygen will be the nucleophile, neutral oxygen with a lone pair. We need an electrophile. Well, we know that a carbon with a positive formal charge is a good electrophile. a carbon with a positive formal charge is a good electrophile. Now that we've identified those roles, we can draw the electron pushing arrows from the nucleophile towards the electrophile. In step 2 of an SN1, the nucleophile joins the alpha carbon. Carbon 3 can still be referred to as the alpha carbon. Now we can draw the products of that step. This arrow tells us to draw a bond between the oxygen and carbon 3. Now, should this oxygen still be bonded to the hydrogen and to carbon 6? Well, yes, because these were all covalent bonds. Remember, we don't break a covalent bond unless there's an electron pushing arrow that tells us to. We break a covalent bond only if there's an electron pushing arrow telling us to break that covalent bond. For example, this electron pushing arrow clearly tells us to break the bond between carbon 3 and the bromine because the arrow tail is on that bond. This arrow tail is not on a bond, so it doesn't tell us to break a bond. So it's very important that the oxygen here should still be bonded to the hydrogen and still be bonded to carbon 6. Do you see here that the oxygen is actually covalently bonded to carbon 6, even though it's written next to the hydrogens? That's the way this condensed notation works. You know that a neutral carbon has to have 4 bonds. So the 4 bonds for this carbon are 3 bonds to hydrogen and a 4th bond to this oxygen, even though they're not written right next to each other in this condensed notation. All right, so make sure that you carry along these other atoms that are still covalently bonded to the oxygen. But the most important part to get right is the charges. Make sure you change 2 charges. The oxygen is at the beginning of the arrow and it started neutral. The oxygen is losing electrons, so it should become 1 step less negative, 1 step more positive. So this oxygen should end up with a positive formal charge. I find that students have a really hard time remembering to put in this positive formal charge. It's a very common mistake to forget to change this charge at the beginning of the arrow, but it's crucial to make sure that you do change this charge. And of course, carbon 3 started positive and gained electrons, so carbon 3 should become neutral. We've already drawn it that way. Now we need to ask whether we're finished or whether we need another step. Now you might think that you're finished because we've done the 2 steps for an SN1 reaction, but actually it looks like we're not finished because our main product still has a formal charge. When the main product still has a formal charge, you usually need to continue the mechanism. Now you can see why it was so crucial to include this positive formal charge. If you leave out the positive formal charge, you would probably think that you're done with the reaction. But we know that we're not done. So now we're going to go on to step 3. So let's do this checklist all over again. Again, we should determine what type of step we're going to do next. Well, a common pattern is if you do the nucleophile electrophile step and there's still a formal charge, the common pattern is to do an acid-base cleanup step to get rid of the formal charge. So we expect now that we need an acid-base cleanup step to clean up the formal charge that was left over from our nucleophile electrophile step. Now we can identify the roles that atoms will play. Focused first on the atom with the formal charge. What role would the oxygen play with a positive formal charge? We know that atoms with positive formal charges are strong acids, because an acid needs to receive electrons, and a positive formal charge makes you want to receive electrons. An atom with a positive formal charge and an attached hydrogen is a strong acid, as we saw in the previous video. Now an acid has to react with a base, so who are we going to use as our base? Now your first instinct might be to use the Br- because it has a negative formal charge, but we've specifically learned that Br- is a very weak base. Most professors prefer that you only use Br- as the base if there's nobody else who's better. What we've actually learned is that when we're using an alcohol as the solvent, it's better to use the alcohol as the base rather than a Br-. So we're going to actually use this alcohol molecule. So I need to write down that alcohol molecule again so that we can use it again in this step. And we're expecting to use the oxygen in the alcohol. as the weak base. It's a neutral oxygen with a lone pair. In the previous video, we learned that when alcohol is the solvent, most professors prefer for us to use the alcohol as the base rather than Br-. Of course, we already used up an alcohol in this first step, but we don't need to worry that we're going to run out of alcohol because the alcohol is the solvent. So there's a lot of these alcohol molecules. We're not going to run out, so we can use another alcohol molecule here as the weak base. Now we're ready to draw our electron-pushing arrows. This is a difficult step for many students. Students often have difficulty drawing the acid-base arrows. It'll help if you just have memorized that the first arrow for an acid-base step is from the base towards the proton. From this base towards the proton. Now I need to redraw this so I can see the bond here. So the first arrow goes from the base towards the proton. That should make sense because a base is defined as something that donates electrons to take a proton. And now the second arrow should be obvious. The acid is defined as something that receives electrons to lose a proton. And this looks good because now at the end of our arrows, we have a positive formal charge. It's good to put a positive formal charge at the end of the string of arrows, like we had here as well. Make sure that it's boringly easy for you to draw the correct electron-pushing arrows for an acid-base step. Only after you draw the arrows should you draw the products from that step. So now we can draw the products from this step. This arrow tells us to draw a bond between this oxygen and this hydrogen. The simplest way to accomplish that is just to say that instead of being OH, this is now OH2. Now it has two bonds to hydrogen. Remember, the most important thing to get right is the charge. This oxygen started neutral and it's losing electrons. So the oxygen should end up with a positive charge. It's crucial to get that charge right. Now this arrow tells us to break the bond between this hydrogen and this oxygen. In a way, I've already broken that bond. So we've broken the bond between the oxygen and the hydrogen, and we changed the charge. This oxygen started positive and it gained electrons, so I've already changed the oxygen to neutral. After I finished recording the solution for this problem, I noticed that I hadn't quite followed my own recommendations here. I recommend numbering all the carbons. Here we have carbon 6, but I forgot to number this carbon. This carbon is also carbon 6. So this carbon is also carbon 6. And following this recommendation, I should have given a number to this carbon. I'll call this carbon 7. This is a new molecule of the alcohol that's going to play a different role in the reaction than the first molecule of the alcohol. So I'm going to give it a new number, number 7. And that means that this will be carbon 7. As a beginning Ochem student, you will make fewer mistakes if you take the time to number all the carbons in your products consistently with the numbers you used for your starting materials. I didn't realize that I had forgotten to number those carbons until I finished recording the solution for this problem. So in the remainder of this solution, the numbers for those carbons will be missing. Now we want to ask, are we done or do we need another step? Well, our main product now has no formal charge, so we're probably done. Here's our main product. We can't get rid of all the formal charges. We couldn't get rid of this formal charge, and we can't get rid of this formal charge, but I hope it's intuitive that those would not be considered the main product. This is what we would consider the main product, and as a problem-solving technique, we can say that when the main product has no formal charge, there's a good chance that you're done with the mechanism. Notice that we used our alcohol solvent first as a nucleophile and then later as a base. That's consistent with our table. Our table here tells us that alcohols can be used as poor nucleophiles and also as weak bases. An alcohol is a poor nucleophile, but still good enough for SN1, which is how we used it. And an alcohol is a weak base as well, and that's how we used the alcohol in this step. It's only a weak base, but this compound is a strong acid. A strong acid can generally react with a weak base. So again, this table confirms that both water and alcohol can be used as poor nucleophiles and also as weak bases. And since they're solvents, we can use them more than once in the same mechanism without worrying about running out of them. So again, here we saw the common pattern of if your nucleophile-electrophile step leaves you with a positive formal charge, you likely have to follow that up with an acid-base cleanup step. Why is this called a cleanup step? What are we cleaning up? We're cleaning up the formal charge. So what are the big mistakes that students often make here? Well, students often leave out the positive formal charge in this step. If you leave out the positive formal charge, you won't realize that you need the acid-base cleanup. So we make sure that you always change the formal charge at the beginning of the series of arrows. We have to change the formal charge at the beginning of this arrow, changing carbon 3 from neutral to positive. We have to change the formal charge at the beginning of this arrow, changing the oxygen from neutral to positive. And we have to change the formal charge at the beginning of this series of arrows, changing this oxygen from neutral to positive. The most common student mistake is forgetting to change the formal charge on the atom at the beginning of the series of arrows. So make sure you get into the habit of always changing that charge. Another mistake that students oftentimes make is I oftentimes see students leave out the atoms here that are connected to the oxygen. Students don't always realize that the oxygen is going to pull all these other atoms along with it. Well, remember, you should only break a covalent bond if an arrow tells you to break it. There's no arrows telling us to break any of those covalent bonds, so all the atoms that are covalently bonded to the oxygen should be dragged along with the oxygen. Most SN1 reactions require an acid-base cleanup step. So now we've learned how to carry out the acid-base cleanup step when necessary after an SN1 reaction. Now you can understand this handout a little better. The handout says that SN1 has two main steps, but besides the main steps, there may also be an acid-base step, and we've seen how that works. Or at least we've seen one way that an acid-base step can be involved in an SN1. In this video, we have discussed how to handle an SN1 mechanism that involves a neutral nucleophile, such as water or alcohol. In the first step, the leaving group leaves the alpha carbon. In the second step, the nucleophile joins the alpha carbon. But then in the third step, when you've used a neutral nucleophile, you need a third acid-base cleanup step to clean up the positive formal charge that was on the main product that was created from step 2. In the next video in this series, we will discuss our next SN1 topic. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.